The topic is power transmission and loss characterization. Here we talk about the power transmitted over a transmission line and represent this power as a function of voltage and current amplitude and determine the power loss in terms of decibel. So here the power transmitted over a specific distance as a function of voltage and current amplitude is given by instantaneous power, and instantaneous power is equals to real voltage into real current. Here the power is determined in terms of voltage and current, and this is the instantaneous power, and instantaneous power can be determined by using real voltage and real current, which means that we take a real part, that is cos term, and instantaneous power means the power is a function of z and t, means position and time. Now to determine the instantaneous power, we use the transmission line equation in terms of net shunt impedance Z and net series impedance Y. So here we take a voltage transmission line equation, and this is a second order one, which is represented as d square v suffix s upon dz square equals to r plus j omega l into g plus j omega c into v suffix s. Here s suffix s is called a sinusoidal voltage, and this value is equal to gamma square into v suffix s, because here we take r plus j omega l, that is called a net series impedance, and g plus j omega c, that is called net shunt impedance. So here the gamma square is the propagation constant and its value is z into y. So here the propagation constant gamma can be written as under root of z into y. So it can be written as under root of r plus j omega l into g plus j omega c. And we know that the propagation constant is a complex quantity. It has a alpha plus j beta term. Here alpha is called the attenuation constant and beta is called a phase constant. Since this is a second order voltage transmission line equation, and the solution of this equation, differential equation, is the voltage, that is a function of z only. And the solution of this second order voltage differential equation having a two terms. First is v naught plus e to power minus gamma z, and second is v naught minus e to power plus gamma z. Here the first term is for forward propagation and the second term is for backward propagation. And here v naught plus and v naught minus are called the amplitude of the forward propagation and backward propagation respectively. So here we consider only a forward propagating term so that we get a finite value of voltage function. So here we take a forward propagating term, and in forward propagating term we have a v naught plus. Here v naught plus is a amplitude, and to determine the real voltage we take a real part of this amplitude. So the real part of this amplitude v naught plus is equals to mod of v naught. Similarly, we can use a real current, and real current also have a two terms which has I naught plus and I naught minus. Here also we take a first term, and in the first term we have I naught plus. I naught plus represent the forward propagating term, and here also we take a real current. For this we take I naught plus equals to mod of I naught, and here mod of I naught is shifted in phase theta. This shifted in phase theta is due to the characteristic impedance Z0. So here we take a transmission line equation in terms of Z and Y, and after getting a solution in terms of real voltage and real current, we get a real amplitude and real current in terms of mod V0 and mod of I0. And here mod of I0 is shifted by some phase theta, that is due to the characteristic impedance of the transmission line, that is Z0. So here both the voltage and current attenuate according to the factor, that is e to power minus alpha z. Because we know that the gamma propagation constant is equals to alpha plus j beta, and here the attenuation constant is alpha. So the voltage and current amplitude attenuate according to the factor, that is e to power minus alpha z. Now we can determine the instantaneous power in terms of real voltage and real current. And the instantaneous power means the power having a function of z and t. But from the above equation we see that the voltage and current equation is a function of z only. So we have to make it a function of time also. For this we multiply by a time factor e to power j omega t. So we get a real voltage and real current. So the real instantaneous voltage is given by mod of V0 e to power minus alpha z cos omega t minus beta z. Here the omega t term is due to the factor e to power j omega t, and the instantaneous current equation is mod of I0 e to power minus alpha z cos omega t minus beta z plus theta. Here the instantaneous current equation is shifted by some phase theta, that is due to the characteristic impedance of the transmission line. So here we multiply instantaneous voltage and instantaneous current to get a instantaneous power in terms of real voltage and real current. So we combine the two terms, we get mod of V0 into mod of I0 e to power minus 2 alpha z cos omega t minus beta z into cos omega t minus beta z plus theta. Here theta is the phase, that is due to the characteristic impedance Z0. So in this way we can determine the instantaneous power. Now to determine the time average power, we integrate it over a period of time t. That is, time t is the time period for one oscillation cycle and its value is 2 pi by omega. So to determine the time average power, we integrate this instantaneous power over a time period t. So the time average power is equals to 1 upon t integration p function of z comma t into dt. Here we take a limit 0 to capital T. Here capital T is the time period for one oscillation cycle. So after putting the value of instantaneous power, we get this equation, and here we can use a formula of cos A cos B, which is 1 upon 2 cos A plus B plus cos A minus B. So the time average power become 1 upon T integration 1 upon 2 mod V0 into mod of I0 e to power minus 2 alpha z within bracket cos 2 omega t minus 2 beta z plus theta plus cos theta. This we get from a formula of cos A cos B, which is 1 upon 2 cos A plus B plus cos A minus B. So we open the bracket and we take a two terms. In the first term there is a cos 2 omega t minus 2 beta z plus theta, and we have to integrate this over a period of time t, and we know that when we integrate a cos term over a period of time, its value is 0. So here the first term is 0 and the time average power is equals to 1 upon t within bracket 1 upon 2 mod of V0 mod of I0 e to power minus 2 alpha z cos theta integration of dt. Because these are all a constant term, so we take it outside the integration. So the integration is with respect to dt only. So after taking the integration of dt and putting the limit from 0 to t, we get a time t, and thus this time t is cancelled because there is a 1 upon t outside the bracket, and we get 1 upon t mod of v naught into I naught mod of I naught e to power minus 2 alpha z cos theta. So this is the time average power, and we know that the characteristic impedance Z0 is the ratio of voltage upon current. So here we take a amplitude term, that is voltage amplitude and current amplitude in real form. So in place of I naught we can write V naught upon Z naught. So we get a time average power in terms of characteristic impedance, which is 1 upon 2 mod of V naught square upon mod of Z naught e to power minus 2 alpha z cos theta. And here the unit of this time average power is watt. Next is we can also determine the transmitted power in terms of phasor voltage and phasor current. So here we consider a phasor voltage and phasor current. The phasor voltage is written as V function of Z equals to V naught e to power minus gamma z, and phasor current is written as I function of Z equals to I naught e to power minus gamma z. Here gamma is the propagation constant, which is equals to alpha plus j beta. So here after putting the value of gamma, that is alpha plus j beta, we get a phasor voltage V function of Z suffix s equals to V naught e to power minus alpha z e to power minus j beta z, and the current phasor is I function of Z suffix s equals to I naught e to power minus alpha z into e to power minus j beta z. And we know that in a transmission line the current phasor having a phase shift, that is due to the current characteristic impedance. So we can write the current phasor in terms of characteristic impedance. So in place of I naught we can write V naught upon Z naught, because we know that the Z naught is equals to V naught upon I naught, that is the ratio of voltage upon current amplitude. So the current phasor is equals to V naught upon Z naught e to power minus alpha z into e to power minus j beta z. And to determine the time average power in phasor form, we take a phasor voltage and phasor current. So the time average power in phasor form is equals to 1 upon 2 real part of V.S. into I.E.S. star. I.E.S. star means complex conjugate. Means when we have to find the time average power in phasor form, we take a complex conjugate of a current phasor, and we take 1 upon 2 of the real part of V.S. into complex conjugate of I.E.S. phasor. Since the current phasor is equals to V naught upon Z naught e to power minus alpha z into e to power minus j beta z, and we know that to determine the complex conjugate we put the imaginary part. We have to change the sign of the imaginary part. So the complex conjugate of the current phasor is V naught upon Z naught star into e to power minus alpha minus j beta into z. Because in current phasor there is an imaginary term, that is e to power minus j beta z, and its complex conjugate is e to power j beta z. Similarly, the complex conjugate of the characteristic impedance Z0 is equals to mod of Z0 e to power minus j theta, because we know that the characteristic impedance has a magnitude and phase, and the phase is e to power j theta, and its complex conjugate is e to power minus j theta. So after putting these values, that is the voltage phasor and the complex conjugate of the current phasor, and also the complex conjugate of the characteristic impedance, we get this equation. And after combining this, there is a phase of the characteristic impedance, that is e to power minus j theta. So this is in denominator term, so we take it to the numerator side and it become positive. So the time average power in phasor form is equals to 1 upon 2 real part of V naught into V naught star upon mod of Z naught e to power minus 2 alpha Z into e to power j theta. And we know that the real part is cos term, and here the exponent term is e to power j theta, so the real term is cos theta. In this way we can determine the time average power in phasor form, which is 1 upon 2 mod of V naught square upon Z naught mod e to power minus 2 alpha Z cos theta, because we know that V naught into V naught star is equals to mod of V naught square. So in this way we can get a time average power in phasor form. And here we see that this power attenuate as a factor, that is e to power minus 2 alpha Z, because 1 upon 2 mod of V naught square upon mod of Z naught cos theta is a constant term, and this constant term represents a amplitude of the power, and this amplitude of the power is attenuate by a factor, that is e to power minus 2 alpha Z, because here alpha is called the attenuation constant. So we can say that the power drops at twice the exponential ratio with distance as either voltage or current, because here the factor is e to power minus 2 alpha Z. So the power drop is twice the exponential rate. So this is about the power transmitted over a transmission line over a specified distance, and this instantaneous power can be determined by using a real power and a real current. The next is we have to determine the power loss in decibel. For this we take a above equation, and here we take a ratio, that is P function of Z upon P function of 0, means this second term is the amplitude of this power, and this attenuate by a factor e to power minus 2 alpha Z. So here we take a ratio of average power upon original power amplitude, and it is equals to e to power minus 2 alpha Z. To convert it into a decibel unit, we decrease this power as a power of 10, which is equals to 10 to power minus k alpha Z. Here k is any constant which is to be determined. So here we see that the value of alpha Z is 1, and we get e to power minus 2 equals to 10 to power minus k, which means that we simply equate the above equation. And to solve this we take a log on both sides, that is log to base 10. The left side is log to base 10 e to power minus 2, and right side is log to base 10 10 to power minus k, and the result is the left side is minus log e square base 10 equals to minus k log 10 base 10, and we know that log of 10 base 10 is equals to 1, and we get k equals to log of e square, and the log of e square is 0.869. So after putting the value of k, we get the ratio is equals to 10 to power minus 0.869 alpha Z, and we have to determine the power loss, that is a ratio in terms of decibel unit. For this we multiply by 10 log to base 10 on both the sides. So after taking the 10 log to base 10 on both the sides, the right side becomes 10 log into 10 to power minus 0.869 alpha Z. Here the log is base 10, and this value, that is 10 to power minus 0.869 alpha Z, can be taken as a multiplication with 10. So here we get a log 10 to base 10 and its value is 1, and the right side is minus 8.69 alpha Z. So in this way we can determine the power loss in terms of decibel unit, and its value is minus 8.69 alpha Z. Also we know that the time average power in the phasor form is directly proportional to mod of V naught square. So we can also write power loss in terms of mod of V naught. As we know that the power, time average power, is directly proportional to mod of V naught square, and here is 10 log to base 10, and when we take a mod of V naught square, it becomes 20 log to base 10 mod of V naught 0 upon V naught Z. So in this way we can determine the power loss in decibel when we take a power in terms of real voltage, that is mod of V naught. So this is about a power transmission and a characterization, that is the power loss in terms of decibel.